Hello and welcome to our next lecture. Today we're looking at convolutions. We have seen that when we talk about solving initial value problems with Laplace transforms, we often end up inverting Laplace transform of a product of two Laplace transforms. So what is the relationship between the functions that created Laplace transforms and the inverse Laplace from the product? And the answer is convolution. Suppose I have two functions that are defined for all positive values of t. The convolution of the functions f and g is defined and denoted as f star g, and that's a function of t defined as an integral from 0 to t of f of t minus lambda times g of lambda d lambda. Note that the t is the outside variable for this integral, and the internal variable is lambda, and the integration is done in terms of lambda. And you might be wondering what kind of meaning this integral has. So to give you a little bit of a visual intuition about the convolution, I created a short mathematical demonstration. So suppose I have a function f of t that is just a portion of t from 0 to 1. So what is the graph of the function f of t minus lambda when lambda is the variable and t is a parameter? If you evaluate it, this is the graph we're going to see. Initially t is 0 for this demonstration, and we see that the function f of t minus lambda has a plot flipped around the y-axis because lambda has a negative sign inside f. And if I start changing t, you can see that it just moves the graph around. And you can see that it moves the graph around in sync with t. If t is positive, the graph moves to the right. If t is negative, the graph moves to the left. Here you can see the values that t is taking. So let's look at what happens inside the integral. What I have is two slightly different functions this time. I have f of t as the tall step function and g of t as a step of size 1, but a bit wider, takes 2 units. So what happens when I start shifting those functions around and multiplying them together? Right now, these functions have product 0 because the two steps do not intersect. When one step is 1 or 2, another step is 0, and their product is always 0. However, when I start intersecting the steps, that's when the product starts to be non-zero. And the product is non-zero exactly where those functions intersect in their domain where they both not equal to 0. If the taller step is completely inside the domain of the wider step, then the product is the same as the function f itself. And when the function f starts to go outside of the domain of g, that's when the step starts to get a little bit narrower. And now the product is again 0. You can see that this is a dynamic process, that the product depends on the amount of shift. And the functions don't have to be step functions. That can be any functions, but it's just easier to see what's going on with this product inside the integral for different values of t. So the parameter t shifts around the function f. The function f has a reverted direction because lambda has a negative sign there. And then we integrate the product for each value of t, and that gives us a value of the function for that particular t. So let's see what happens when we start integrating. So I define the convolution to be the integral. Now let me see what's going on. So I'm integrating from 0 to t, and if t starts to get positive, that's when my functions start to get a little bit of an intersection. That's when the integral starts to get a little bit positive. If I make t smaller, then the intersection is going to be tinier, and the value of the function is going to be smaller. And then I record the value of the integral for each value of t. On the bottom set of axes, I'm drawing the function only from 0 to t, although the evaluation for that particular t happens right there at the end. So the current value of the integral is about 1/2. Start moving t around, then the intersection reaches the point where no matter how I change t, the product is always having the same area under the graph. So for this part of the integration, the product always results in the same value. The area under the graph is 2. As soon as the function f starts to go outside of the domain of the function g, the intersection reduces itself, and therefore the value of the integral drops. And then finally it drops to 0. So this is how a convolution integral is computed. It takes two functions and creates a new function. And the value of this convolution depends on all possible products of f and g together, evaluated for different shifts of the function f and g against each other. So the convolution is just another operation. As an integral operation, it has some properties. One of the properties of the convolution is commutative. It doesn't really matter if you put g first or f first. So the f star g of t is exactly the same function as g star f. We can prove that with employing change variables inside the integration. So if I change the variable to say tau is t minus lambda, then lambda becomes t minus tau, and d tau is minus d lambda. For the limits of integration, tau has got to be t. And for the second limit of integration, tau is 0. So this changes the integral into integral from t to 0 of f of tau g of t minus tau times minus d tau, which changes in the integral while flipping the limits of integration and introducing another minus sign. It becomes 0 to t f of tau times g of t minus tau d tau, which is exactly the convolution of g with f. Another property is that convolution is linear. That's a consequence of the fact that integration operation is linear. So if I take a function f and compute a convolution with a linear combination, of two other functions, then that's going to be the same as the linear combination of convolutions. This property is easy to prove with properties of the integral. Also, convolution is associative. Which means that if you compute the convolution of three functions, say you compute the convolution of g with the function k, and then you compute the convolution of f, that's going to be the same as first computing the convolution of f and g, and then computing the convolution with k. The easiest way to prove this property is to employ the convolution theorem, which we're going to cover right on the next page. This property says that if we compute the convolution of several functions, it doesn't really matter in which order we compute the convolution. The convolution theorem is one of the cornerstones of the signal analysis. It relates the convolutions of the functions in time domain to the products of the Laplace transforms. And here's what it says. Suppose I have two functions. And suppose my functions have Laplace transforms f of s and g of s. Then the Laplace transform of the convolution is simply the product of the Laplace transforms. Brace yourself for the proof, as it involves some advanced multivariable calculus. By definition, the Laplace transform of the convolution of f and g is the integral from 0 to infinity of the convolution, which is the integral from 0 to t of f of t minus lambda, g of lambda, d lambda. And this big integral is multiplied by e to the minus st. I can join these integrals into one double integral from 0 to infinity and from 0 to t of f of t minus lambda, g of lambda times e to the minus st. That's integrated with respect to lambda and with respect to t. If you looked at the set over which we're integrating, then this is the picture. Lambda goes from 0 to t, so for each t, lambda covers the interval from 0 to t. And t goes from 0 to infinity, so as t grows, the interval over which we integrate grows as well. So this is the set over which we're integrating. What I want to do is I'm going to introduce a change variable. I'm going to say that u is going to be the same as lambda, and v is going to be the same as t minus lambda. So in essence, what I'm going to do is I'm going to shift this set a little bit down. You can imagine this as sort of a set of vertically stacked cards, and then I'm kind of shifting them down so that they become flush with the table. So the old variables can be expressed in terms of new variables this way. T is therefore becoming u plus v. The boundaries of the set I have here can be described as lambda equals 0 and then lambda equals t, or t minus lambda equals 0. This changes the boundaries for my new set in my new coordinates u and v into u equals 0 and v equals 0. Therefore, in uv coordinates, I'll be integrating over that set. Change of variables in multivariable involves computation of a Jacobian. Which is the determinant of the matrix d lambda du, d lambda dv, dt du, and dt dv. Computing these partial derivatives gives us d lambda du is exactly 1, d lambda dv is 0, dt du is 1, and dt dv is 1, and the determinant of this is 1. Therefore, d lambda dt is exactly the same as 1 times du dv. By changing the integral, my Laplace transform becomes the integral from 0 to infinity in terms of v times the integral from 0 to infinity in terms of u. And I have f of v times g of u times e to the minus s multiplied by u plus v. And then integrated with respect to u and then with respect to v. I'm going to break the exponential part into a product and write f of v with e to the minus sv together and g of u with e to the minus su together. This can be easily seen that it can be written as a product of the integrals, because now the integrand is completely decoupled. I have an integral of f of v times e to the minus sv dv times the integral of g of u times e to the minus su du. And this is exactly the product of the Laplace transform of f times the Laplace transform of g. Alright, this proof was a bit longer than the proofs we considered before, but this is the main takeaway. If we multiply the Laplace transforms, what happens in the time domain is the convolution. We can use this to find the convolutions. For example, given these two functions, f of t equals t and g of t is just a step function that goes up at t equals 0 and down at t equals 1, their convolution is not that hard to find. And let's go ahead and try to find the convolution by definition. When computing the convolution, we have to decide first which function we're going to shift. And I suggest it's easier to shift the function t. Since h of lambda is always going to be 1, we can change it to 1. And the function h of lambda minus 1 is going to be 0 until we reach lambda equals 1. So we can break it into two intervals. When t is from 0 to 1, f star g just integrates from 0 to t the function t minus lambda multiplied by 1 minus 0. So it's just an integral of t minus lambda, which is minus t minus lambda squared over 2 evaluated from 0 to t. Here we must understand that the integration happens with respect to lambda, not with respect to t. Plugging this in gives us minus 0 over 2 minus t squared over 2. So it's just t squared over 2. When t becomes larger than 1, the convolution becomes the integral of 1 minus h of lambda minus 1 d lambda. And what we get here is that h of lambda minus 1 will turn everything to 0 as soon as lambda reaches 1. And since t is greater than 1, this will always happen inside the integral. So any integration that happens from 1 to t is going to be 0. So it's going to be the integral from 0 to 1 of t minus lambda times 1 minus 0 d lambda minus the integral of 1 to t of t minus lambda times 1 minus 1. The second integral becomes 0, so we only need to evaluate the first integral. So as before, the antiderivative is t minus lambda squared over 2 with a negative sign, evaluated from 0 to 1. When we plug in 1, we get minus t minus 1 squared over 2 minus t squared over 2. Simplifying this gives us t minus 1/2. Therefore, the convolution of f and g can be expressed as a piecewise function. It's t squared over 2 for t from 0 to 1, and it's t minus 1/2 for t greater than 1. If you try to plot it, then this is what this function is going to do. It's going to evolve as t squared over 2, and then once you reach 1, it's going to continue as a straight line. We can compute this convolution using the Laplace transform. So for t, the Laplace transform was 1 over s squared. And for the function h of t minus h of t minus 1, the Laplace transform is 1 minus e to the minus s over s. The convolution can be computed as the inverse Laplace transform of the product of these Laplace transforms. So it's the inverse Laplace transform of 1 over s cubed minus e to the minus s over s cubed. 1 over s cubed is the Laplace transform of t squared over 2. And the second one is just a shift of the same function. So it's minus t minus 1 squared over 2 times the Heaviside function of t minus 1. When t is less than 1, the Heaviside function will zero everything out, and the t squared is going to be the value of the function. When h of t minus 1 becomes 1, this expression will simplify into t minus 1/2. So we get exactly the same function in the result, except it was a lot faster. Before we go further, I'd like to mention a few things. So if you remember, for first order differential equations, use the integrating factor method, and the solution can be written as e to the minus at times the integral from 0 to t e to the positive a tau times f of tau d tau, which you can write as the integral from 0 to t of e to the minus a times t minus tau times f of tau d tau. So you were doing convolution integrals without even realizing that. The same goes with the variation of parameters formula for systems of differential equations. So the convolution integrals are not something new to you. It's just now we decided to put a name on it. In some applications, you may have to do multiple convolutions. So if you're given a function that's a convolution of several functions, so you have f1 in convolution with f2, which is in convolution of f3, etc., 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 in convolution with fn, then you can compute your function y by using the inverse Laplace transform on the product of the Laplace transforms of each function. And it might be easier doing it this way. As an example, let's consider a convolution of 3 functions. Each one of them was just a function of t. So the Laplace transform of each one of those is just 1 over s squared. Therefore, the convolution can be written as the inverse Laplace transform 1 over s squared times 1 over s squared times 1 over s squared, which is simply the inverse Laplace transform of 1 over s to the 6th, which is the Laplace transform of t to the power 5, except that the 5 factorial is not on the top. So this equals 1 over 5 factorial of t to the 5, which is t to the 5 over 120 for t greater or equal than 0. We can try to do the convolution integrals here, but I'd rather do them with Mathematica. So I need to compute the convolution of the first 2 t functions. So it's going to be t minus lambda multiplied by, I'll replace t with lambda, and I integrate with respect to lambda from 0 to t. If I evaluate, I get t cubed over 6. And now we need to compute the convolution of this function with another function t. And I want to take this opportunity to say that it doesn't really matter if you shift t cubed over 6 or you shift t. And I get t to the 5 over 120. Had I chosen to put t cubed over 6 first, and do the convolution this way, I get exactly the same result. Sometimes the equations we have to deal with involve convolutions themselves. For example, this equation involves a convolution of cosine with the antiderivative of y. It looks very complicated until we write it as a convolution. Get y of t plus 3 times the convolution of the cosine with the antiderivative of y. Computing the Laplace transform gives us the Laplace transform of y plus 3 times the product of the Laplace transform of cosine, which is s over s squared plus 1, times the Laplace transform of this integral, which is 1 over s times y of s. This equals to the Laplace transform of 1, which is 1 over s. Solving for y of s gives us 1 over s divided by 1 plus 3 over s squared plus 1. Which simplifies into s squared plus 1 over s times s squared plus 4. The inverse Laplace transform one quarter over s plus 3/4 of s over s squared plus 4. Which becomes 1/4 h of t plus 3/4 cosine of 2t. And for t greater than 0, h of t can be replaced with 1. Another type of problem convolution can help us is solving equations with nonlinear integration like this one. We can see that the integral here is the convolution between the function e to the minus t and the function y squared. So we're going to say that f of t is a function y squared of t. And then we have the equation in this form. The convolution of e to the minus t with f of t equals 5 e to the 4t minus e to the minus t. Applying Laplace transform, we get that the Laplace transform of e to the minus t is 1 over s plus 1 times capital F of s should be the same as 5 times 1 over s minus 4 minus 5 times 1 over s plus 1. So f of s becomes 5 times s plus 1 over s minus 4 minus 5. This simplifies into 25 over s minus 4. And as a result, f of t is just 25 times e to the 4t. And as a result, y of t as a square root of f of t is going to be plus or minus 5 e to the 2t. Of course, Laplace transform is not going to help us with every nonlinear equation that we might have, but we can see how helpful it is in this case. Alright, let's look at the last example for today. This equation is a little bit more complicated, involves derivatives and integrals at the same time. Equations like that occur very often in control theory. If you heard combination of words proportional integral derivative controller or PID controller, these are kind of equations we have to deal with. Alright, let's apply Laplace transform to this equation. First, to rewrite this equation as the equation with the convolution. We have y prime plus the convolution of e to the 2t with y. That's equal to 1. After applying the Laplace transform, we get s times y of s minus 0, which is the initial condition for y, plus 1 over s minus 2 times y of s. And they should be equal to the Laplace transform of 1. Grouping the terms together, we get that s plus 1 over s minus 2 times y of s equals 1 over s. And therefore y of s is simply s minus 2 on the top over s times s minus 1 squared. Computing the partial fraction decomposition gives us minus 2 over s plus 2 over s minus 1 plus minus 1 over s minus 1 squared. And therefore y of t is going to be minus 2h of t plus 2e to the t minus the inverse Laplace of this term. It must be the moment of the function e to the t. You can also verify it with Mathematica if you want to. So you can see getting the solution for this integral differential equation wasn't really that hard with the Laplace transform and with the concept of a convolution. Later on we're going to see that the concept of convolution is going to play a huge role in the topic of Fourier transform and signal analysis. So this is not the last time we're going to see the convolution. For now, this is it. Thank you for listening, and I'll see you in the next video.